of the thermistor at a higher temperature. So I just wanted to add to our discussion. So we said that the resistance of RTDs increases with increase in temperature, whereas thermistors decrease with temperature. So we just look into the mechanism. So the question is why resistance of RTDs increase with increase in temperature, but that of thermistors decrease with increase in temperature, but then finally it will increase with increase in temperature. So typically these RTDs are made of metals. And as you know, in metals, the number of electrons per unit volume of the conductor is nearly independent of temperature. So as you increase temperature, the number of electrons per unit volume may not change. But if you talk about the relaxation time, that means how frequently the electrons oscillate inside the metal. The relaxation time actually varies with temperature. And when the temperature increases, basically two things that happen. One is the thermal speed of electrons should go up because electrons movement is linearly proportional to the temperature. They would vibrate faster, so they would move faster. But the amplitude of vibration of the positive ions, which are not mobile, unlike electrons, would also go up about their mean position. So these electrons, when they try to move through the metal, would collide more frequently with the positive ions because the positive ions is now oscillating much faster. The electrons are also trying to move faster. So they would experience much higher resistance to their flow, right? So that is the reason why the resistivity of the conductor basically increases with increase in temperature, because there is a lot of resistance to the flow of electrons coming from the enhanced vibration of the positive ions in the metal. In case of thermistors, the mechanism is slightly different. So thermistors are basically oxides of nickel, cobalt, and so on. So these are basically semiconducting materials. In semiconducting materials, the number of free electrons per unit volume would increase exponentially with increase in temperature. So that is known theoretically that as you increase temperature in semiconducting material, the number of electrons would increase exponentially. So this increase in the number of free electrons at lower temperature basically compensates for the small decrease in the relaxation time. So the net effect is that as you increase temperature, the resistivity would decrease because you have more and more electrons which are coming up and trying to move. So the resistance would decrease with increase in temperature. But as you go to very high temperature, they would behave similar to RTDs, meaning the relaxation time effect would dominate over the increase in the number of electrons. So that means the resistivity would again try to increase with increase in temperature. So that basically explains what happens at the material level, that this behavior that we see here is exhibited by RTDs and thermistors. Okay, so yesterday when we stopped, we were actually talking about thermistors. I think we did talk about RTDs. So we were talking about the characteristic of thermistors. We said that the resistance changes non-linearly with temperature, and a typical relationship is shown here. And from there, you can actually find the temperature just by adjusting the different terms. And here the beta, the value of beta is between the range 3000 to 4500 Kelvin. And the exact value depends on the material and the temperature that we are talking about. So as we said, you can actually find the sensitivity, which is basically if you differentiate this equation and you try to find dr over dt and divide by r, so you would actually get minus beta over t square. You can do it for yourself and find out. And for given values of beta, let's say it is about, we take somewhere in the middle, 4000 Kelvin. And let's say the temperature is ambient temperature to 98 Kelvin. So the sensitivity one can find out would be around 0.045. And this is, you can say that more than 1 order of magnitude higher sensitivity than that of a typical RTD, which is, this is about 0.0035 per Kelvin. Okay, so we now know that thermistors are much more sensitive compared to RTDs. And higher sensitivity is always desirable because it results in larger output, good accuracy, and resolution. But you can have a similar problem like an RTD, that you may have self-heating. So you need to really limit how much current that flows through the RTD when you actually do the measurement using your circuit. So this is just an example. Let's say you have a thermistor circuit here. So you have a power supply, and you are basically measuring the output here. And let's say the thermistor has a resistance of 5000 ohm, and it is capable of dissipating 1 milliwatt with 1 degree increase in temperature. So the question is, if the temperature to be determined with an accuracy of 0.5 degrees centigrade, the power should be limited to 0.5 watt. Then what should be the current? Right? So the current you can find as power divided by resistance square root, because I square into R will give you the power. So you take the square root of power to resistance, and you say that you have to operate at something like 316 microwatt. Now we know that the characteristic of thermistors is nonlinear. As we said, the resistance exponentially decays with increase in temperature. As you can see here, this is for a real thermistors. Somebody has actually done the measurement and plotted here. So the question is, I mean, we really do not want nonlinear system. I mean, when you want to develop an instrument, you prefer to develop a nonlinear system. So if you have bought a thermistor and you can actually build a circuit to make the net response of the circuit linear, something like this. So this is the thermistor, and so you can have a shunt resistor here, and basically to limit the amount of current. In parallel to the thermistor, you can have this RP, a resistor, and the resistors are basically made out of metals, and their resistance would basically increase with increase in temperature. So that is contradictory to thermistor. So you can see here, this would be the typical response of the thermistor. But the resistor will have a response of something like this, right? The resistance would increase with temperature. So you should pick a resistor such that the net effect of a decaying response and an increasing response would give you a linear response, something like this. Okay, so you can pick an RP, a resistor which has a temperature characteristics just to compensate for the non-linearity of this thermistor, so that you can have a linear characteristic. So it is possible to do that using a circuit, control circuit, something that is shown here.
Sir, what exactly does RS do here, the shunt resistance?
So, I mean, this is basically to reduce the amount of current that is flowing through the thermistor, right? So, if you can see that, you want to limit the current that is actually flowing through the resistor, otherwise you'll have the I square RT problem. So this resistor basically tries to limit the current that flows through the thermistor.
Yes.
But what is important here is that you can use a resistor in parallel to the thermistor to make the characteristic linear.
Sir, because of this, any error compensation gets added up, or like?
See, I mean, the objective here is that can we build a linear system, right? Linear systems are always preferred because, if you know a value of resistance at this temperature, you know the value of resistance at this temperature. And if you measure, as the temperature changes, the resistance will change. So if you have some kind of resistance measured, you can predict the temperature. So you always need to, I prefer to have a linear characteristic. So that is the objective here. Of course, I mean, when you introduce a new resistor here, you talk about equivalent resistance, right? And basically you studied about error propagation, right? So when you have two different resistors, definitely, there will be some measurement error from here, there will be some measurement from here, and your error would propagate. But even if you have error, you have a linear system, right? So that is something that you want to achieve.
I could not gather this point that by adding RP, we will be able to achieve the linear characteristics
so
of
you
the
can
system.
imagine, like, you have a decaying curve, right?
Right,
so
sir.
if you have a resistance which have an characteristic something like this, you can imagine that you have basically these two are in parallel, right? So you find an equivalent resistance for this, and so that you get the equivalent resistance to be a linear function of temperature. So basically you have to design the RP such that it compensates for the nonlinearity. Okay. So you can do this mathematically, right? You can, if you know this linear characteristic and if you know this nonlinear characteristics, you can very well find out what should be my RP dependency with temperature that gives me a linear characteristic.
Okay, point by point mapping can be done.
Yeah,
Right.
yeah. You can create a curve and which would basically represent RP.
Thank you, sir.
Right. So now I talk about thermocouples. So we talked about RTDs, resistance temperature detectors. We talked about thermistors. Now we talk about thermocouples. Thermocouples are very important. It's probably the most commonly used temperature sensor across. So we will spend some time talking about thermocouples in detail. So thermocouple basically comprises two dissimilar materials, and not any material. They have to be thermoelectric material in thermal contact. Okay. So, and what we mean by thermal contact? By thermal contact, we mean that they form what is called junction. So you can create junction between two materials or metal wires together by welding and soldering and brazing and so on. This is typically the circuit representation of a thermocouple. So you have one metal wire here, A, material A, and the second metal wire B. And you basically join the ends of these two material. Let's say you solder and you create a junction here. And then the other end, you solder here and create the second junction. Now you have two metal wires. So typically one is negative, one is positive. We will talk about what is negative, what is positive in a while from now. But typically you cut upon the positive wire, and so you have basically an open circuit. So you measure this open circuit voltage here. An EMF that is induced in this circuit can be measured. So when you maintain these two junctions at two different temperatures, okay, typically one of them is at some reference temperature. Most widely, you use the reference temperature as ice point temperature. Sometimes you use this as the ambient temperature. And this is the reference temperature is mostly used as the cold junction. And the other junction, which is in contact with the surface or the environment whose temperature you want to measure, is typically known as hot junction. And I mean, in this example, if you have T1 greater than T2, then you will have the direction of current as shown. And of course, the direction of current would depend on the material combination. And so we'll talk about what are the materials that are used for thermocouples and what is positive material and what is negative material shortly. But the essence is that whenever you have a temperature difference across the two ends, two terminals or two junctions, you will have a current that is flowing through the circuit, and that current basically gives rise to this EMF. So the thermocouple basically operates on what is called thermoelectric effect. So what is thermoelectric effect? So thermoelectric effect basically is categorized into Seebeck effect, Peltier effect, and Thomson effect. And it is known that a combination of Peltier effect and Thomson effect gives rise to what is called Seebeck effect. So if you see this circuit here, as we discussed, there is a small open circuit voltage that is generated when you have two different junctions, J1 and J2, maintained at two different temperatures, T1 and T2. Okay, and this is known as Seebeck effect. The moment you have two different temperatures at two different junctions, you will have an EMF that is generated. So this thermoelectric voltage can be generalized as a nonlinear function of temperature. So you say that the output voltage V0 here is some constant C1 into the temperature difference between the hot and cold junction, plus this would be C2, plus C2 into T1 square minus T2 square. So where these constants are called thermoelectric constants, and then depend on the materials, these material A and B that are used to form junction. Okay. So you can define what is called Seebeck coefficient. Seebeck coefficient basically represent if you have a 1 degree difference of temperature between the hot and cold junction, the corresponding EMF that is generated is basically the Seebeck coefficient. Okay, so it is, in other words, it is basically the rate of change of the output voltage with the rate of change of temperature difference between the hot junction and cold junction. So alpha S, which stands for Seebeck coefficient, is basically dV, the output voltage, dV or not over dt. So from here you can understand that for a given temperature coefficient, temperature difference, if Seebeck coefficient is higher, that means the output will be higher. So you essentially, this is kind of the sensitivity of this temperature sensor. If Seebeck coefficient higher, then the temperature sensor is, that thermocouple is more sensitive, because for a small change in temperature, you get a large output. So what is that causes this current? So typically you have two different materials. I said material A and material B, and you basically solder them or braze them, fuse them to create this junction. And when you form this junction, since they're thermoelectric material, so the electrons from one of the material will jump across the interface into the second material. Okay, and the material that is receiving this electron is negative with respect to the material that is giving away this electron. Okay, so we'll talk about negative material and positive material, thermoelectric material very soon. And this diffusion of electron would actually depend on the temperature. And since the diffusion of electron is a function of temperature, then as the temperature change increases, then there will be more and more diffusion of electrons across this interface, and hence your output voltage is going to increase. So that is the reason this thermoelectric material respond to a higher temperature difference across the junctions in terms of higher EMF, because there is stronger or more enhanced diffusion of electrons across this interface that take place.
So, sir, the phenomenon that you're telling is similar to the electroplating electrochemistry, same thing, right? The electron movement.
Yeah, so typically you have transfer of electron from one metal to another metal. Yeah, I mean, typically in electroplating, you have transfer between the electrolyte and the material.
Yeah.
Yes, but here it is from one material to another material. Okay, so we talk about Peltier effect. What is Peltier effect? When you have when you have two different wires forming two different junctions, junction J1 and junction J2, if you pass a current through this circuit, this closed loop that comprises of two different thermoelectric materials, the property of these materials are such that when there is current passing through, heat will be absorbed at one of these junctions and heat will be released from one of these junctions. Okay. And this effect is known as Peltier effect. So it says that when current passes through a two-junction thermoelectric circuit, it leads to heating of one junction and cooling of other junction. This is known as Peltier effect. So the heat absorbed or released at junctions is given by this expression. It is the QP is the heat, amount of heat that is absorbed here and released here. And that is given by the Peltier voltage by subscript AB stands for the Peltier voltage times the current, which is I, that is flowing through the circuit. So you can see that this is positive when the heat is basically getting released from the system, and it is negative when the heat is absorbed into the system. And you can actually find out the net of heat rejected to heat absorbed, and times the given the net heat transfer, which in terms of Peltier voltage will be positive for the heat absorbed and negative for the heat release, and that times the current. So then we have Thomson effect. Okay, so you have Thomson effect, which talks about a single current carrying conductor. So you have a single current carrying conductor, and you have 2 points, T1 and T2. Current is flowing through it. If you have a current flowing through a thermoelectric material where the ends are a different temperature, T1 and T2, that means there is a longitudinal temperature gradient from point 1 to point 2. Heat will either come into the wire from the ambient or go out from the wire to the ambient. Okay, and this heating or cooling effect is known as Thomson effect. So you have a current carrying conductor with the ends at different temperature, and the wire itself is basically getting heated or getting cooled, right? So if T2 is greater than T1, the electrons are actually moving from the region of high temperature to the region of low temperature. This is the direction of current. So electrons are moving in the opposite direction. So the electrons are essentially moving from the region of high temperature to low temperature. And in that case, heat will be rejected from the wire. And the heat rejected is given as the current times the Thomson coefficient into the incremental temperature dT integrated from T1 to T2. Okay. And similar expression can be written for the other conductor, conductor B. Let's say this is for conductor A. The other conductor, you will see that there, if this is going from high temperature to low temperature, there high temperature for the second one. So that will have a negative sign here because the heat will be absorbed for the other one, because now the direction of current is from low to high. Direction of the electron is from low to high, so this will be negative. So the net heat exchange between the wire and the surrounding can be found as the current times the sigma A minus sigma B into dt integration from T1 to T2. So basically now you can say that my net output in a typical thermocouple circuit, we said that the Seebeck effect is a combination of the Peltier effect and the Thomson effect. So typically in a thermocouple circuit, when you have two junctions and you have two different temperatures maintained at two different junctions, then you get the total EMF that is generated, the open circuit voltage, is going to be the sum of the Peltier voltage that you get for this system plus the Thomson effect that you get for this system. Yeah, so we are talking about thermocouple materials, right? So these are different thermocouple materials that are most commonly used, and these are typically, listed in a certain order that we will talk about. And depending on the temperature range that you're interested to measure, you can have something that is measuring close to 100 degrees centigrade, not very high as 500 degrees centigrade. Then you have another list here. And if the temperature is close to 900, you have another list that is showing up here. So basically, the combination would depend on the temperature range. The thermoelectric materials, wires, right? So you can, for example, pick iron and constantan, for example, or copper constantan, right? So when you pick copper and constantan, let's say, it says that all materials that are listed below, that are below a particular material are negative with respect to one under consideration. So that means if you consider copper, for copper, all other materials that are listed below copper are negative with respect to copper. That means we talked about what is positive, negative here, right? So if this is copper, constantan is below copper. So that means copper will basically give away electron and constantan will receive electron, negative with respect to copper. Okay. So this is what it is. And same is the silver, and anything that is below copper here are negative with respect to copper. But you can see that if you take, let's say, iron, copper will become negative with respect to iron. Okay. So, for example, for antimony, iron will become negative with respect to antimony, and so on. Now, what is also important is that the Seebeck coefficient, which is proportional to the thermoelectric power, that means higher is the Seebeck coefficient. For a small change in temperature, you get higher EMF. The Seebeck coefficient actually increases as the row count between the two materials increases. That means if you take antimony and copper, and compare with the Seebeck coefficient of antimony and chromyl, antimony and copper will have higher Seebeck coefficient than antimony and chromyl. So for antimony and bismuth, will have the highest Seebeck coefficient compared to, let's say, anything else there with respect to antimony. So farthest the two materials are on this column or this column or this column, higher will be the Seebeck coefficient. Okay, so these are few standard thermocouple types that you would see in the lab. And each type, they're basically coded: B type, E type, J type, K type, R type, S type, D type. So each type of thermocouple have a specific material combination. Okay. For example, J type is made out of iron and constantan. And they will have, each of these materials are also coded in terms of color. So iron is typically will be coded in iron constantan. Iron will be coded as white and constantan will be coded as red. Okay. So you can see that T type, you have copper coded as blue and constantan as red. So mostly just by looking at the thermocouple wire combinations, you will be able to tell what kind of thermocouple it is. You can see that B, E, J, K, T, they're all in, very different combination. R and S tend to be similar kind of combination because in terms of the composition, they're very close. So this has platinum and rhenium 8713 and S has 90 and 10, and we have platinum here. So this is for p-type, the Seebeck coefficient is very low. Okay, and you can see that E-type has the highest Seebeck coefficient, followed by J-type, and then T-type, and then K-type, and then S and R. Okay, so this you can represent here. So x-axis is the temperature, y-axis is the output voltage in millivolt. So you can see that like if you can compare here, so you see that type E, where the Seebeck coefficient is the highest, so that has the highest slope, right? So Seebeck coefficient is basically representative of the slope of the output versus input of a thermocouple. So this is type E, and type K and okay, type N and G we are not discussing here. So type K is here. Type J will also be somewhere here, close to J, and type S is here. Okay, it has a small slope. So we say that the larger is the Seebeck coefficient, higher is the sensitivity. E-type has the highest Seebeck coefficient, the highest sensitivity. G-type has the highest temperature range. So if you can see G-type, it goes from 0 to nearly 2500. And sensitivity of K-type and T-type thermocouples are comparable. And K and T-type are most commonly used in laboratories because they have linear characteristics, and they're also inexpensive as compared to other type of thermocouples. So most academic labs, they use either K-type or T-type thermocouple. So either you will have chromyl ulmyl or copper constant. Okay. Now, use of thermocouple. So typically, as we said, there will be a wire which is positive and wire that is negative. And so typically you have a measuring junction, and this is the EMF instrument, typically a voltmeter. So from the measuring junction, you have the P-type wire running to the voltmeter, and then from the voltmeter you have another the same P-type wire connects to the coal junction, and then the negative wire basically connects here from the hot junction to cold junction. So basically, as I said, the open circuit voltage is measured in the P-type wire. Okay, so you cut open and put this voltmeter there. Okay, so you will see that the measuring junction typically is at higher temperature. So this is basically you connect to the source whose temperature you want to measure. Reference temperature, normally it is either dipped in ice or it is just hanging in the ambient. And in fact, everywhere else, so like these two terminals which form because you have cut the wire and put in the voltmeter. So these two junctions will be typically at ambient temperature. So if I plot the temperature variation along the length of the wire, so I have a length of the wire here in the x-axis, temperature in the y-axis. So this is basically the hot junction temperature, which is Tm, or measuring junction temperature, Tm. And this is basically the ambient temperature, which is where the voltmeter is connected. And you can see that temperature along this P-type from here to the voltmeter would reduce something like this. And then from here to here, temperature will be constant. And from here to here, the temperature will again reduce and reach the cold junction temperature. which may be, let's say, ice point, right? 0 degree. Similarly, the N type would basically reduce from here to ambient, because, certain part of the wire will be at ambient. So it will reduce to ambient and then again reduce to the reference temperature. So this is typically how the temperatures would vary across the wire length of the wires in a typical thermocouple circuit. So we have to understand that the thermoelectric effects that contribute towards the EMF generation, which helps you in basically predicting the temperature, is confined to only the junctions. That means these junction temperatures are very important. So these ambient temperatures or isothermal temperatures elsewhere, which you see here, do not contribute anything towards the thermoelectric effects. So depending on the application, thermocouple wires can be very long. Okay, let's say you have some big machine and you cannot, of course, take your voltmeter inside the machine, and the control system is outside, and you are trying to measure temperature of a certain region of the machine, which is, very much deep inside, and you have to inevitably use a very long thermocouple wire. So thermocouple wires are typically expensive. And so when you do not want to waste these, special thermoelectric material wires, in the isothermal region where the temperature is not really varying, you can, in fact, replace this thermocouple wire with copper wires. So you can have the P type and N type, and you can have a measuring junction. And after some length, you can use copper all the way till, again, very close to the reference junction. Then you can use the P type. And similarly, on this side, you can use the N type. Then you can use copper and then N type. Okay, so this way you will be able to avoid using long thermocouple wires if that is of concern. So similarly, like the previous case, here you can measure the temperature. So this is basically the hot junction, the measuring junction temperature. And on the P side, the temperature reduces. So this is where the isothermal region, right? So there you are replacing by copper. And then again, in P type, the temperature is reducing the reference temperature. On N type, similarly, here the temperature is decreasing to ambient, remaining ambient, and then decreasing to the reference temperature. So I will talk about laws of thermocouple circuits, then we'll stop. So laws of thermocouple circuits, the first law is the law of homogeneous material, right? So it says that you need at least two junctions formed by two dissimilar thermoelectric materials for the thermocouple to work. And so you must have material A, you should have material B, which are thermoelectric materials, and you must have a hot junction, you must have a cold reference junction or cold junction. Right? It also says that the output only depends on the junction temperatures. Okay, so the output is strictly a function of temperature T1 and temperature T2. It doesn't matter what the temperature is in the intermediate regions. Okay, that is important to notice here. The second law is the law of intermediate material. It says that if I have a thermocouple material, so you have material A here and you have material B here, and material B, let's say, is positive, so you have the open circuit voltage being measured here. It says that if I cut upon the material A and introduce a third material, material C, then it is not going to affect the output. So it says that the output is not affected by insertion of a third metal into a leg. So that is the reason why you will be able to use copper, because it is not going to affect your measurement. So this is coming from law of intermediate material. It also says that you can even not have a junction between material A and material B, but a third material, material C, which is basically sort of forming the junction here, provided the entire thing here is at a fixed temperature. Okay, it is almost like the wire is isothermal. So it says that output is not affected by insertion of a third metal into a junction. Then you have law of successive temperatures or materials. So law of successive temperatures tells that if I have material A and I have material B and my temperatures are T1 and T3, whatever output I get, let's say it is V0, 1, 3, then I can have another scenario where I have material A and material B, but the temperatures are T1 and T2. And in the second case, I have material and material B, the temperatures are T2 and T3. So it says that the output for the junctions at temperature T1 and T3 will be equal to the sum of outputs for when the junctions are at T1, T2 and T2, T3. So basically V0, 1, 3 will be equal to V0, 1, 2 plus V0, 2, 3. This is called law of successive temperatures. There is also law of successive material. Law of successive material tells you that if I have material A and material B, with the temperatures always fixed, T1, T2, T1, T2, T1, T2, whatever output I get here will be the sum of if I have material A and material C and material C and material B. Okay, so V of the output when you have A, B will be equal to V output AC plus V output CB. Okay, this is known as law of successive material. Right, so I will stop here, and if you have any question, we can discuss.
Sir, one practical question. So I think batch 1, I mean, sorry, 2023 batch, we recently
Recording
attended
stopped.
Yeah,
practicals, and during one of the experiments wherein it was like a tribometer, I think, yeah. Wherein there was a thermocouple which was used to measure what is the surface temperature between the pin that is put on the disc which is rotating. So in that case, what observation came out is the temperature was recorded in one of the data acquisition system, which is the ideal. Sir, if you can just slightly go to the previous slide,
yeah.
or the previous one also, I'm sorry, wherein there is a circuit, yeah, 29 slide.
Okay.
Yeah, so here, so my understanding is that voltmeter is part of the data acquisition system. So what
Yeah.
the lab instructor or the person who was there was doing is he just he just put one of the ends of the thermocouple into the machine and it was able to measure it. But it was not at the direct point of contact of the pin and the disc. The temperature was able to be measured. And the other method in which he was measuring the temperature was he was flashing an IR light on it on the exact point of contact, and there was a temperature which was coming out. The
Yeah.
thermocouple output was somewhere around 30.3 degrees Celsius, but the IR sensor output was around 33 degrees Celsius or 32 point something.
Yeah.
So there was a variation. So my query is that what is the understanding based on this circuit and the physical experiment? I mean, wherein we are putting the actual measurement point somewhere else. How should I correlate that with respect to the thermocouple? Can you just?
Yeah, so I mean, I don't know whether I understood your question correctly. You are saying that there are two different methods that are used to measure temperature. One is using thermocouple and other using air camera. So, and they tend to give you two different temperatures.
Yeah, one part of
And
the question maybe you can tell whether the measurements based on the two different instruments, why it is going to be that different.
yeah,
Second part
I
of the
do not know really, who did the measurement and whether the instruments are working properly or not. I have no idea.
understood. Okay, maybe
Okay.
whether the readings would be different, whether that question can be.
See, reading should not be so different, right? If you have done the measurement correctly, whether it is air camera or it is a thermocouple, the temperatures I don't think can differ by few degrees. You are saying, no, 30 degree and
30.3 and it was 32.3, I believe.
Sorry, sir. The answer is actually initially we forgot to position the sensor properly. Then later only we came to know that sensor was not in the right position.
So that is the
That's-
I'm saying that between two different methods, I mean, my experience has been that if it is within plus minus 1 degree, I can tolerate. Okay, I mean, depending on the calibration, the way IR is calibrated and the way thermocouple is calibrated, less than 1 degree is tolerate. One can tolerate. That is my experience. But if it is few degrees, 2 degrees, then there must be something wrong. Okay. And I mean, in this particular case, I really do not know what
Okay, sir.
gone
So
wrong.
maybe we can focus on the next part of the question, wherein I want to just understand this particular image on this slide, the practical thermocouple circuit
Yeah.
versus what is actually done in a actual instrumentation point of view.
Yeah.
So,
So
maybe
this is very similar to what you do in an actual thermocouple circuit. I mean, when we do experiment in our lab here, so we have this kind of arrangement. In fact, there is a mechanical engineering lab as part of which we do the temperature measurement, where these students basically use the measuring junction. They bring in contact with the surface, whose temperature they want to measure. And the reference junction, they dip it in ice. So they take, ice in container, and they know that, okay, they have a thermocouple to also, the thermometer to say that, okay, it is at 0 degree. And so that is the reference junction. And then you have a voltmeter, which is connected. So, I mean, this is very much identical to what somebody would use in a practical thermocouple circuit.
got it, sir. So if I'm trying to correlate it correctly, in the example that I was trying to quote, Tm would be the surface temperature that I'm trying to
Yeah,
measure.
yeah.
The
Tm would
cylinder
be the
bin and the
surface temperature. Your TR, I don't know whether he would have used ice or he would be just simply hanging in the ambient.
it was simply hanging and it was ambient.
If it's just simply hanging, the problem is that, see, when the ambient condition is well controlled, let's say you have a controlled lab environment, that means the temperature is not changing so much, right? But if you do not have a controlled environment, suddenly, there is the sun comes out and then there is heating, or somebody switches on the fan. Your reference junction, if it is not stable, then your measurement will not be stable. Your data will be erroneous. So it is
And
important
yeah,
to
got it.
ensure
So and
that,
TA would be
yeah, your TR, you have to make sure the TR is fixed. It is not changing.
got it, sir. But TA, where will TA be measured? It will be internal to the instrument
Well,
only. Will not be
TA is not important really. TA is just, I just mentioned here, you are not really measuring temperature TA here. That is just ambient temperature. I mean, it may be little higher, little lower, that doesn't matter. So TA is basically, see, you have the copper wire coming and then you have this, the voltmeter wire, right? So it is not really important to talk about.
Thank you, sir. Clear.
That is that is this law that tells you, right? I mean, it doesn't matter what is the temperature in between here. What is
Yes, yeah.
important is the measuring junction temperature and the reference junction temperature. If the reference junction is simply hanging around in the lab and this itself is fluctuating, and I mean, then this will also be, it will not be correct. Okay.
Sir, also, sir.
Yes, sir.
Yeah.
Sir, sir, our exam is on 6th. You told me that some assignments will be given to us. So is it possible?
Yes, yes. So, I mean, we are today on 25th. So I would certainly give it to you. Can you please send me an email so that I don't forget? So I should, maybe I can give it to you tomorrow if you can send me an email. Okay.
And also some slides also, whatever.
Yes, some slides. And so please send me an email so that I would.
Sure, sir. I will do, sir.
Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Sir, hello.
Yeah.
Sir, one more doubt I have, sir. Like you mentioned that this thermocouple works on the reference temperature basis. Suppose if there is a variation with the reference temperature, if the ambient temperature is varying, how will be measured? And also, like adding to it,
See, that is
we
why
have some.
the
Yes, sir.
reference temperature need to be a controlled temperature, something that you know and something that will not change. So, I mean, a ideal way of doing it is use some ice, right? Or
Okay, sir. So
yeah.
Yes, sir. So means generally we have some industrial thermocouple type sensors, like even thermocouple type switches also available, which are without giving any reference, it gives the results. So how that works, sir?
Okay,
in
okay.
that
So then
context?
I will. So that will be covering in next class. Okay. So
Okay, sir.
when
Okay, sir.
you are not really trying, there are some applications where you do not want to keep the reference junction fixed. What
Yes.
you do is that you use what is called differential thermocouple. So there it is the temperature difference delta T which is important, not the absolute value of the reference temperature. Okay, so I will talk about
Understood, sir.
that in the next class.
Understood, sir. Thank you so much.
Hello, sir. Yeah, thanks for sharing that. But I just want to know your opinion, because we have used some system to measure the vibration. Like I forgot the name of the instrument, and along with that, it has got the thermocouples. So does it does it use the similar differential thermocouples, or it will measure
Yeah,
the
so if you are not worried about the reference junction, it must be a differential thermocouple.
Okay. Okay, sir. Yeah, thank you.
Because otherwise, the ambient with the reference junction is just changing, then you will get, erroneous results. So typically in instruments, or you would have to use differential thermocouple. So I'll talk about that in the next class.
Okay, sir. Yeah, thank you.
Yeah, I was talking about from point of view of doing experiments in a lab, where you can very well, put your reference junction at a fixed temperature. But that is not possible in an actual machine. So there you have to use the differential thermocouple.
Sure, sir. Yeah, thank you.
Okay, so if no further question, then we will meet next week. Thank you. Thank you very much.
Thank you, sir.
Thank you,
Thank
sir.
you.
Thank
Thank
you.
you, sir. Did sir end the class?
Yeah, yes.